I've spoken about special relativity for quite a few videos, and I'm going to stick with that subject matter here too. The last handful have focused on relativity basics and how clocks tick differently for different observers. But there's another counterintuitive consequence of relativity that confuses the heck out of people. This is the idea that different people see lengths differently. I mean, how can that possibly be? I bet you know that I'm going to tell you because, well, you guys are smart that way. Before I start, I should tell you that this video has an actual derivation. Sorry about that. But it has something even more important. It first uses relativity wrong, but in a way that seems right. Then I identify the mistake and redo things properly. This is a super important thing to see because it's so easy to make mistakes in relativity. The good thing is that the math is pretty easy. We just start out with the standard Lorentz transform equations. As a reminder, those are the equations that you see here. If you've not seen them before, I talked about them in my video on what relativity is all about. Take a look at that video if you like, or you can just trust me and we can press on. Remember what these two equations mean. We have two observers looking at a situation. For one of them, the situation isn't moving. For the other one, the situation is moving. Typically, we say the person seeing the situation not moving is the unprimed observer, and the moving person is the primed observer. So, in this situation, all we want to do is measure how long a stick is. Now, this just doesn't sound all that hard. I mean, like, there's a stick, and I measure how long it is, and there you go. I mean, how hard is this? Like, am I wasting your time or something? Well, I hope not, because you have some experience measuring a thing that isn't moving, but you've probably never measured the length of something moving at an appreciable fraction of the speed of light, have you?
So what happens when you try to measure something in motion that can actually act out in basically a different density, or I would argue it's a different dimension. However, it's acting out in a way that a fluid would, because the whole universe actually acts out as a fluid, and so you have different viscosities, and every different viscosity would be a dimension unto itself. Now, we're stuck being humans. We are not designed to understand an abstract world. However, the way in which we do start to try to learn abstract is to try to relate it to something easy for us to understand. So, how would it look like if I was underwater and a giant boat was there? And what would happen if that boat started moving faster and faster and faster?
Well, no, of course not. Sorry, dumb question. But now, let's be a little careful about how you measure something. The way you actually do this is to find the location of one end of a stick and then the other end of the stick and then subtract those two locations. Suppose you had a meter stick and you
Suppose you had a boat and you're underwater and you measured it.
labeled the ends A and B. You could put end A at location 1 and the other at location 2, which we'll call x1 and x2. x1 could be at position 0, then x2 would be at 1 meter. Subtract the two, and you find that the meter stick is indeed 1 meter long. Now you could have picked other locations. x1 could have been at 98.3 meters, which means that x2 would be at 99.3 meters, and if you subtract those, again, you get 1 meter.
And if you have a boat moving slow enough, well, if you have like a boat, if you're measuring a boat and it's moving at a constant speed, then its base measurement would be the same, right?
Yeah, I know. All of that was painfully obvious, but trust me, it's about to get a little more mind-bending. So let's just ask ourselves what a moving observer thinks. And to do that, we're going to exploit the Lorentz transforms. I'll tell you what, let's make it more interesting and not use a meter stick, but rather some stick with an unknown length that we'll call L. Let's say that the unprimed observer, which I remind you is the one who sees that the stick not moving,
So you're underwater. You're looking up at the boat.
decides to do the measurement at the time equals 0. Suppose further that she puts one end of the stick at location 0. Then, rather obviously, the other end of the meter stick is at location equals L. Putting this in terms of x's and t's, we would say x1 t1 equals 0, 0, and x2 t2 equals L, 0. So let's put those into the Lorentz transform equations and see what the primed observer sees. For location 1, you get the same 0, 0. But for location 2, you get x2 equals gamma L, and t2 equals gamma v over c squared times L. Pushing ahead, you could then subtract the two x's according to the primed observer, and you'd get that the length according to the primed observer would be L prime equals gamma L. Since gamma is greater than 1, that would mean that the moving observer would see a longer length than the stationary one. But before you get that in your head, let me draw your attention to something very, very important. Look at T1 prime and T2 prime. T1 prime is 0, and T2 prime is gamma v over c squared times L. Remember that those are times, and they're not the same. That means that the primed observer didn't measure the location of both ends of the stick at the same time. And since the stick is moving according to the primed observer, that's not the way to measure its length. You totally not get the right answer. It doesn't make sense. Okay.
Unless you're realizing that for things to go to a certain speed, they have to start moving into a different, basically, viscosity, density. Call it a different dimension. Light is primarily traveling at a separate dimension. That's the reason why it can go that fast. And be unaffected, because most of it's like what you consider like mass or whatever is actually playing out in a different dimension that is not the same as time space as we experience it right now. However, the best way to try to argue a visualization of this would be to go back and think of yourself as someone underwater. Now you have a ship, and we already know this, with viscosity or density, okay? The ship is floating on the surface of the water. It's displacing itself. So, to an observer, it's a bigger object, displacing much more mass. However, the faster it goes, the less it's doing that. And it actually looks like it's getting smaller and smaller and smaller. Now, looking up, and from you could see the reverse if you were like on the boat trying to observe things in the water too, because you're trying to peer down in something that has a slightly different dimension. So it's a misunderstanding of how time-space is interacting with us versus at a slightly either different dimension or a different viscosity. Either choice. You can think of that as a different, basically, density of time-space. That's one reason why you can see objects in the quantum world pop in and out at the same time. It's the same object. It's there. It's just acting out in different time space. So you're seeing it act out. Basically, the same object act out two different places in our density. But it's existing outside of our time space. So, like that argument where you see things pop in and out would be like more like if I took a rock, you're still that guy underwater, and I skip a rock. If I skip it fast enough over the air, it can look like that rock has now hit multiple places. It's the same rock. From my perspective, I can even sometimes you can actually see what appears to be the rock in the water due to like reflection. And so you can have the exact same rock from our perspective. You can be staring at all of it. And it now looks like, how is it in 2, 3, 5 different places? Well, we're in a different dimension or viscosity or however you will prefer to try to argue this.
So now we get to the very crux of the matter.
And what's acting out?
And this is a biggie. Two events that are simultaneous to the unprimed observer, the one who doesn't see the stick move, is not simultaneous to the primed observer. That just sounds weird, but it's true. It's also a big reason why people dallying with special relativity make so many mistakes. So, the second thing is that if we want to measure the length according to the primed observer, the one seeing the stick move, we need to simultaneously measure the locations of both ends of the stick according to the primed observer. There are lots of ways to do this, but I think this way might be the clearest. Let's start by just subtracting the two positions in two times according to the primed observer. The length L prime is just x2 prime minus x1 prime, and the duration, big T prime, is t2 prime minus t1 prime. We can write that out using the Lorentz transforms, and we get what you see here. It's just the Lorentz equations, but with the positions 1 and 2 subtracted. Okay, maybe this is getting a little mathematical, but it's just these two equations. So, remember what we need to do. We need to have the primed observer find the location of the two ends at the same time. And that means that t2 prime equals t1 prime, which means that the left-hand side of the bottom equation is 0. We want to get rid of the times and only have locations, so we can solve for t2 minus t1 and get this here. And we can take this and put it in the top equation, and we get this equation that we see here. So, we can factor out the gamma in x2 minus x1. Now, remember, the gamma is 1 over the square root of the quantity 1 minus v squared over c squared. That means that 1 minus v squared over c squared is equal to 1 over gamma squared. So, we can substitute that in and get this equation here. And finally, we can cancel the gammas and get this equation. And that brings us to the answer. We replace the differences for both the primed and unprimed variables with the L prime and L, and what we find is that the length of the stick in the primed frame is the length in the unprimed frame divided by gamma. Since gamma is greater or equal to 1, this means that the person who is moving with respect to the stick sees a shorter stick than one who is stationary to it. And using the fact that both observers...
Sure. I'm hanging out here on a boat with someone else. We're just cruising along. Nothing changes. You change how the dimension, the viscosity, from the original person is, and it looks like this, and it's acting out from our perspective like that.
Can claim that they're stationary. This means that a moving stick is shorter than a stationary one. Now, there's one important thing to remember, and that is that the shrinking only occurs in the direction of motion. There's no shrinking side to side. This means if you start with a basketball and accelerate at high speeds, it'll look like a pancake. Still round in the direction perpendicular to the motion, but flat parallel to the direction.
Because we're viewing it. There's ways of trying to
motion. And this is real. We see it when we do experiments smashing together the nuclei of heavy atoms in our colliders. I made a video about the quark gluon plasma in which I mentioned this effect. It also means something really weird. Suppose that you had a stick that was 40 feet long and a barn that was 20 feet long with doors on both ends. If you got the stick moving at a little over 86% the speed of light, then gamma is 2. This means that the stick would be 20 feet long according to the person seeing it moving. That means that it's possible to, for a split second, put a 40-foot long stick in a 20-foot long barn and close the doors. Bizarre, huh? Now that might sound like a paradox. I mean, after all, a person who was sitting with a stick would say that the barn had shrunk. But remember that the two observers don't agree on when things are simultaneous. So while one would say the barn doors were closed at the same time, the other wouldn't. There is no question that this weird effect really occurs, but people often have misconceptions about it. Many people accept that the stick might shrink, but they don't think that space changes. But that's the wrong way to think about it. After all, when I did the derivation, the stick didn't come into play. All that mattered was the x and t positions of the end of the stick. Take the stick away and you still have x's and t's. So this length contraction, which has been measured, is a powerful reminder that relativity really does mix space and time.
Okay, but the better way to think of this, visually, and the one thing everyone seems to be missing out is, it's because it's going into a different dimension or different viscosity. Like, if you're trying to move at a lower even if it's not a full-on dimension until you get to a certain speed, to be able to get to that speed, you're basically up in a different dimension, okay? That's what I'm arguing. Now, if I'm at the bottom of the ocean, it's actually harder, because of all the pressure, to move as fast as a less dense area. So even within the ocean, you have this like range. So within our reality, we have this range. And so the way in which to move faster is we got to go up in this, up, so that the viscosity is less, slowing us down. There's like less pressure, less friction affecting us, basically, of time. Okay? So, however, this is just our little dimension of reality. It's of this range of viscosity of time space, okay? So, there are things acting out completely at different viscosities, aka different dimensions. And the quantum universe by itself is in fully a different one. And this is just a better way to try to conceptualize what's acting out here. And once you are able to better visualize it, then you can better understand something. If you can try to like relate it to something that we can just kind of slightly comprehend, even though time space is a viscosity is kind of an abstract concept. But the best way to visualize it would be densities of liquids. And then we can do that. To an observer, what would a boat moving faster and faster be? And why is it doing that? Because it's technically, for a split second, not necessarily displacing as much. It can still have, you could probably still measure it, and sometimes you could still see the same mass or whatever until you raise up to a really high thing, and then its mass starts being displaced completely out of this density, which is what I would argue the conversion between mass and light and energy, etc. is just an object going into basically another density or dimension in a way. Either way of how you'd want to argue it. It might not be, you might want to have a more rigid form of dimension, and so its mass is being like not shown in our level of density of time space for X amount of period of time. And then if you can convert it back into something, then yeah, it's acting out how we would form mass. Anyways, thank you. God bless. Take care.